We're going to look at a simple harmonic motion problem. And the type of simple harmonic motion we're going to consider is mass on a spring motion. So I've got a mass, I've got a spring, and if I pull the mass down and I let it go, it bounces up and down. We know the crucial piece about simple harmonic motion is that it repeats over and over and over. And so an important fact about the system is this: how much time does it take for the motion to repeat? That's the period. We're going to look at a simple harmonic motion problem, and ultimately the thing we're going to have to find is the period. But let's look at the problem and then see how it corresponds to the actual motion we see in front of us. But let's look at a problem statement. A cup with mass 95 grams is suspended from a long spring. When an additional 35 grams is added to the cup, the spring stretches by an additional 18 centimeters. The cup is pulled down 5 centimeters below this new equilibrium position and released. How long will it take the cup to return to its starting point? Now let's look at the physical system that we have here. We don't have a cup. We've got a little figure with a backpack that we can put mass in. And it turns out this mass is 95 grams. And if I add an additional 35 grams, and I'm adding 35 grams by adding 7 American nickels. An American nickel has a mass of about exactly 5 grams. And if I add an additional 35 grams, the spring stretches by an additional 18 centimeters. If we measure it, that's what we'd find. So the physical situation we have here corresponds to what we saw in the problem. Now, here's what we're asked. We put additional mass inside the cup. We pull it down 5 centimeters below its equilibrium position. We let it go. And the question asks, how long will it take the mass to return to its starting point? In other words, how long will it take for the mass to go from here, up, down, and back to where it started? Well, that is just the time for one oscillation. That's the period. So the problem's asking us, what is the period for this motion? Now remember, simple harmonic motion for mass on a spring, there's 2 important variables. One is the spring constant of the spring. How stretchy is the spring? The other is, what's the mass that's in motion? Okay? Those are the 2 pieces of information that we need. Now, we aren't told the spring constant. We aren't told the spring constant, but we are told this. We are told that the mass has stretched the spring. Additional mass is added to the system, and it stretches by an extra amount. So we can use that information to figure out what the spring constant is. We're also told what the mass is. We've got the spring constant, we've got the mass, we can compute the period. Those are the pieces that we need to do. Let's look at the problem and see the pieces of information that we need. A cup with mass 95 grams, that's going to be important, is suspended from a long spring. When an additional 35 grams is added to the cup, so there's another mass, the spring stretches by an additional 18 centimeters. That's going to be important pieces of information. Let's take that and let's get started. Okay, let's do some preparation for solving this problem. We know it's a mass on a spring problem. And ultimately, what we're computing is the period for a mass on a spring. Well, we remember the period for mass on a spring is given by this expression. T is equal to 2 pi times the square root of the mass divided by the spring constant. So really, we have 2 things to think about. We have to think about the mass, and we have to think about the spring constant. These are the 2 pieces that we need to solve. Let's think about the mass first. What is the mass that's oscillating? What do we want to use in this expression? Think about that. We're going to give you some choices. Let's go back to our problem statement. The problem statement said we had an original mass of 95 grams. To that was added 35 grams. In our expression for simple harmonic motion, when we compute the period, the mass is the total mass that is oscillating. And the total mass that's oscillating is the 95 grams plus the 35 grams. We have a total mass of 130 grams in motion. That's the number that we need to use. But of course, we need to put it in kilograms. So the mass that we use, 130 grams, 0.13 kilograms. Now, let's come back to our equation. In our equation, the next piece that we needed to solve for was the spring constant. What is the spring constant? Well, we aren't told what the spring constant is, but we are told how much the spring stretches when mass is added to it. So to solve for the spring constant, we're going to have to think about the physics of that stretch. Let's do that. Let's make a picture. Okay, we start with a mass hung from a spring. It's at equilibrium. Now, we take that mass and add to it. So I've taken that mass and added a little bit. And because of that, the spring stretches an additional amount. And this additional stretch of the spring we call delta L. That's the change in length of the spring. And we know what it is. It's 0.18 meters. That's the additional stretch of the spring. Now let's think about our expression for the stretch of a spring. The force, the restoring force of the spring, is equal to the spring constant times the change in length. Well, in this case, the change in length that we're interested in is the additional stretch of the spring. That's a number that we have. That's our 0.18 meters. But the question is this. What do we use for the force? What is the additional restoring force of the spring? Now we know it's a weight force, but there's a couple of weight forces we could have. Is the weight force we're interested in the weight of the original mass, the weight of the extra mass that we've added, or the weight of the combined mass? Which one do we want? Think about that for a second. Let's think about this. The length that we're using here, the 0.18 meters, that's the additional stretch of the spring. Because the spring was stretched by 0.18 meters, it applied a restoring force. And the restoring force that it applies is equal to the additional force applied to the system. That's the weight of the additional mass that we've added. And so what I'm looking for is the weight of this 35 grams of additional mass. Weight force, m times g, 35 grams, times our value for g, we end up with the weight force, the additional force, 0.34 newtons. And that's the value that we need to use for the force in this expression. So now that we have the force, now that we have the change in length, we can calculate the spring constant. To do that, let's rewrite our expression for the spring force. We're going to do it to solve for k. The spring constant is equal to the force, that's the restoring force of the spring, divided by delta L, that's the change in length of the spring. Well, the restoring force, the extra restoring force, 0.34 newtons, divided by the change in length of the spring, which is 0.18 meters. And so we end up with a spring constant of 1.9 newtons per meter. That's our spring constant. At this point, we're done with preparing, and we can go back and we can solve the problem. Remember what we're solving for. We're looking for the period. And the period for mass on a spring is 2 pi times the square root of the mass in oscillation divided by k, the spring constant of the spring. The mass in oscillation was the total mass of the system, 0.13 kilograms. The spring constant we just calculated, 1.9 newtons per meter. And so we have everything we need to solve for the period. And if we do that, we get a period of 1.6 seconds. Now the most important step. Let's look at this 1.6 seconds and ask ourselves, does this make sense? Is this a reasonable value to calculate? Let's take a look. The final piece of the puzzle is to look back at our answer and see if it makes physical sense. We've got a mass, we've got a spring, and the variables that we used to calculate the problem are the variables which we see in front of us. There's a mass of 130 grams, and it's on a spring with a spring constant that we determined. We calculated a period of 1.6 seconds. If I take this, bring it down, let it go, that seems about right. Let's measure to see if it's exactly right. 1.6 seconds. 5 cycles of 1.6 seconds is 8 seconds. So if I let this mass bounce up and down 5 times, it should take 8 seconds. 1, 2, 3, 4, 5 cycles, exactly 8 seconds. And so the answer comes out to be exactly what we expected, which it should. Physics is about the world.